Welcome, everyone. Today we're talking to Peter Adamczyk, an associate professor at the University of Wisconsin-Madison in the Department of Mechanical Engineering. Peter brings biomechanics and robotics together, developing clever mechanisms and advanced algorithms that promise to improve both assessment and treatment for individuals with mobility impairments. Tune in to learn more about how these cutting-edge technologies could impact clinics of the future. And now, here's Peter Adamczyk. Hi, Peter.
Good morning, Josh. Nice to see you.
Yeah, it's been a while.
It has.
Thanks for joining the podcast.
Yeah, my pleasure.
Yeah, so you and I go way back to my PhD days when you were at the time focused on commercialization at the company you founded with my PhD advisor, Steve Collins, Intelligent Prosthetic Systems. This had a strong impression on me, the experience working together and, having this sort of dual academic commercial advisors. It's impacted a lot of my entrepreneurial journey, and I'm excited to interview you today because it's not often I get to talk to someone who's lived on both sides of the academic industry divide. Yeah, I live in it today, and I'm trying to build bridges there. So I think you could share quite a bit over the next hour with our audience about some of the decisions you've made and areas that you've made advancements. I thought maybe let's kick us off with a general overview of your kind of career to date from your perspective.
Sure. Where do I start? So my main field is biomechanics, but it's coupled in with robotics, as you mentioned. So it kind of goes way back to undergraduate years when I was a senior at Case Western Reserve University in mechanical engineering. That was my first exposure to the biomechanics. And I was actually working at the time on a project that it involved an exoskeleton before they were called exoskeletons. We referred to it as a trunk, hip, knee, ankle, foot orthosis, a THACAFO. Okay. And this was with Dwight Davey and the group at the Cleveland VA over there as well. And they were working on a system that was FES powered, so you would stimulate the muscles, and they had a certain number of subjects that they had done a computer implanted stimulation system with. That was the power source. They could make people walk, but only about 10 steps at the time. And so they were looking for a way to conserve power, shunt it around the body to different places. And so that was the mechanism that we were working on. And so I did the preliminary or conceptual design for a hydraulic-based system for that. And that was a lot of fun, a great project to work on as a senior in college. And that was really my first entree to biomechanics. But the funny thing is, really, it didn't stick. So, or it didn't stick at the time. I went off to graduate school at Michigan thinking I want to study cars, which is totally different, of course. I got there. Yeah, so I got there and I didn't study cars. Like I wound up studying, doing simulations of wheeled mobile robots. And after doing that for a while, that was pretty fun, right? I learned a lot about robotics and mechatronics during the course of that. Although the simulation side really didn't strike my fancy, and I started looking around again for what was interesting, and sort of got fished out of the pond by Art Quo, my advisor and your advisor's advisor, right? And I got back into biomechanics by way of a summer project. That summer project was about foot shape and how that can affect walking, how you can make people more or less economical using rounded feet, and how that can be independent of the traditional energy storage and return properties that are considered so important in a prosthesis. That snowballed into initially a pilot test, then a real experiment, then a modeling study, and then several extensions of those, then a prosthetics design, then a company based on the prosthetics design, and more of those. And that became my early career. So by the time I completed a PhD there, we had launched this company, Intelligent Prosthetic Systems, like you mentioned. We had a couple of small business grants to develop the prostheses as well as some of the science associated with that. And it was a nice confluence of work on the small business side and the academic side to do, on the one hand, the development and visioning of where these things might go as products, and on the other hand, the science underpinning that. And so that was my life and career in prosthetics. So design of devices, specifically semi-active devices. That's a word I know you and I have kicked around quite a bit. There was also a big chunk of work on wearable sensors. Both of those are still big aspects of my ongoing work. And then, of course, you and I worked together as you were fleshing out what we called Superfoot at the time, and has turned into many of the things that Humotech does, right, based on your own great efforts to push it. That brought us together to about 2015 or so, and at that point, I sort of looked at myself in the mirror and realized that for my own preference, I was always asking the next question, scientific question, not business question, right? And that was what caused me to realize, oh, you, buddy, you're an academic. You should go be one. And so that landed me here at Wisconsin, where I've been very pleased to arrive. And heck, that was 8 years ago. So I've carried on and tried to expand that. And, back to biomechanics, combining with that robotics.
I definitely want to talk about the future and some of your more recent work, which I'm not as savvy on. But while we're looking into the past, I want to ask some questions about, kind of that journey of prosthetic development, because it seems like for a long time, I mean, that was your life. You were all in on developing this advanced foot, and that experience really helped to kind of lay the foundation for what I picked up and started to build. And up until today, you're still working on prosthetic foot development. I mean, in kind of different directions, but it seems like you have always had ideas for prosthetic feet, cooking, and in various stages of development. I'm curious. It seems like your first instinct was to start a business, with the Caesar foot, which maybe you can elaborate on a little bit, because I think that'll be interesting to some of the audience who doesn't know you already. At any point, did you kind of think about, well, maybe licensing or partnering with an established company? And I'm curious your view of that today, because I guess today you're not likely to start another company.
I will not anytime soon will I be starting a company for that particular thing, although the ideas are still there. So yes, the short answer is yes. Thought about that kind of thing. It's obviously not that easy to execute, and so that's a whole different sort of thought process of how one goes about, partnering with an established firm, licensing and so on. At the time, the technologies that we were exploring, and I'll even say that that's still a current statement to claim that those technologies are still way outside the box, even though we've done a lot with them scientifically over these years. They're very, very different than anything that's out there in the marketplace. And so it was conceptual exploration. It had a potential for application, but it was hard to get people to bite or commit or recognize for sure that this was the right thing to do. May not have been, right? So we were exploring a new space. And what I mean by that new space is this idea that you can make a system mechanically adaptive without making it a full replacement for a leg. And so that's that semi-active type device that I mentioned before. These days there are a few such things, ankles that will change a position but can't actually push your body weight or control a hydraulic system inside, something of that nature. These were still different from that in terms of controlling another property, or in the case of the controlled energy storage and return foot, had several latches and switches that were electromechanical in nature to shunt the energy flow from one side of the foot to the other, and one section of the gait cycle to another. So it was just way outside of the box. And so we did a bunch of work, but it's far enough outside the box that I think convincing an established company that has product lines and tradition to go with it is a challenging thing, right? To be disruptive in that way. It's also mechanically difficult to make it work, reliably and flesh out the appropriate controls for every different thing a person might do in life, make those automatic. It's just a big animal, right?
You've always sort of been ahead of the curve with some of these ideas, which, you're describing the challenges with that. But I've also always been impressed with like the level of biomechanical insight that is built into the devices that you've kind of brought to light. And you've always taken, kind of the testing and evaluation of the concepts very seriously. While I think we've not seen many of these type of products commercialized to date, and it's sort of been a while for those of us that have been working in this field, I feel like it's still more relevant now than ever before, because I think we've all woken up to the fact that, just slapping a motor on a leg and using smart controllers to power that motor is sort of not necessarily going to be a winning approach. That motor tends to be heavy, the batteries tend to be heavy, the gear train tends to be loud. There's sort of all these problems with the traditional robotics approach to powering a joint. So I think, winning ideas, next generation ideas are going to require cleverness in mechanism design and kind of realizing efficiencies related to kind of the biomechanics of gait and the mechanics of the machine. You're still at it. Maybe you could share a little bit about some of the latest concepts.
I'll start with is related to your statement about paying attention to the mechanics of gait and how that interacts with the mechanics of the device. So the whole idea of these semi-active devices is that there are two radically different states in the body when a person is up on their feet, right? One is when your weight is on that foot and it has loads of about 1,000 newtons on it. And the other is when you're not on the foot and it has loads of negative a few newtons. It's hanging there, right? So the other direction of load, or just call it zero, depending what you want to do with it. And so that's a huge difference in the mechanical state inside the whatever linkages or support structures you have. And that presents opportunities that I've been trying to exploit with the work. So the first thing I did in my own PhD work was this was called a rock and lock foot, and that had it had a rounded shape when you were walking on it, and when you stopped, it would tweak some little mechanisms, and when you picked your foot off the floor, everything would snap into place, and it would be a concave shape that gave you a nice heel-toe contact for firm ground stability, essentially. And then when you start walking, it flipped the mechanism back the other way, and when you stepped on it the next time, it would snap into the rocking shape, and you'd be walking again. That was one version of a mechanism where that was sort of a walking versus standing change, and it was that weight on, weight off difference or discrepancy or state change that allowed the mechanism to move. Since then, there are two or three things that we've been working on. One of them is this idea of variable stiffness prostheses. And so this is it's again in the space of mechanisms that control themselves when the foot is off the ground. So that enables you to use actuators that are really less than 50 grams in most cases. I think the first one that we built used an actuator was about 10 grams, right? So really lightweight stuff. And that was because it would move only while you were, while you had your foot swinging for, 40-ish% of the gait cycle, right? And the other idea that I love to build into these things is what I call set it and forget it kind of things, where if you're going to move from one steady state type of behavior to another steady state behavior, be that walking or standing or a terrain transition or from level to up or down hills, you can make an adjustment, but then you get to keep it for a while. And that can be very energy efficient. And so this is sort of an aspect of, okay, we recognize we need different properties, but we don't have to do anything on a real continuous basis with the control of this device. We're going to make tweaks. And so you can imagine that makes your battery go from this big to that big, potentially, and gives you the ability to sort of reduce the power and attention that your controller has to pay to it, and the complexity of all that, while still giving people a pretty substantial benefit. So that variable stiffness foot was essentially intended to adapt to up and down slopes, and potentially some of our dreams are for it to handle things like sand, or reducing stiffness for when it detects that the terrain is uneven and you just don't want to be shoving the body in random directions based on stepping on rocks and roots, for example. So that's one. And then there's another project we have, which is a little bit different, more active, even though it still doesn't push the body around, but it's a 2-axis adaptable ankle. And so the idea here is that any mechanics that comes back from the ground to the body is a combination of the properties of the ground, the geometry of the ground, properties of the foot, the geometry of the foot, and one key thing that is a piece of prosthetic care in any standard case, which is alignment. And so that's the thing you get, right? You can, if you ask a prosthetist, they can fix almost any problem with an alignment change. Raise the toes, raise the heel, shift the foot inside, outside, forward or back, turn it a little bit. We're trying to give plantar flexion, dorsiflexion, and inversion, eversion adjustability essentially to this prosthesis, and have it do it live during swing phases, so that if you get, say, a bad moment at the ankle on one step, it would make it an adjustment to cancel that out on the next and future steps. And so you can see some of the benefits, of course, are this adaptability. Limitations are that it's always one step back, if you will. So we're trying to give it also a little bit of a future-oriented awareness based on sort of understanding the environment that it's in. But that's a little bit of a
fascinating. So you commented earlier about how licensing technology to a established company is easier said than done. Certainly, I agree. I'm curious, from your perspective, what are the kind of primary blockers that you've experienced in this process? To an extent, obvious that, we're trying to bridge the valley of death here, and it's hard for both sides to go too far out on a limb. But I'm curious, from your kind of personal experiences, what have been kind of the top hurdles that you've run into?
That's a great question, and I can't tell you that I have a fantastic answer for it, because I've just never gotten far enough down that road to understand all of them. So far, from my own perspective, it's a question of how far is far enough to actually for anyone to make that leap, right? So, we do these academic prototype kind of things to see how they work, but they're a far cry from the robustness that you would need in a commercialized device, right? One that's going to get into market and go home for 5 million steps with a person. There's a sort of a different flavor of engineering that has to go into the systems. When you're creating the first one, you're trying to really minimize the weight, or you're trying to, do something, whatever it is, for the first time. And in the terms of answering scientific questions, that's enough. But then in terms of getting it out into the real world, that's not even close to enough. And so I think there's a different style of team. There's a different regulatory framework. There's just everything about the approach needs an entire other layer before anybody can bite on it to actually take it towards market. So you either got to have something that's compelling enough that you can convince that partner to sort of put up their own resources, or put up with a delay while a team reorganizes for this different style of push. And I think that's probably the biggest thing from concept to practice, is just recognizing when it's proven enough that you want to commit, and then going ahead and doing that.
I wonder if the challenges with durability are particularly challenging for the area that you're working in, because you're focused on building this sort of extremely lightweight, mechanically clever mechanical systems, where building something that can sort of survive 1 or 10 or 100 steps may be a hurdle that you can clear within an academic setting. But then building that same thing that can last for 2 million cycles, which is sort of the industry standard number, is quite another undertaking. Not impossible at all, just resource intensive. Have you considered, or like, where does it become challenging to put in a lot of cycles in a academic setting? Have you, like, do you run into limitations with subjects and recruitment? Have you considered, building mechanical testing apparatuses in the lab?
I'll say that before you get to the human subjects, which is absolutely a challenge, or consider setting up a mechanical test device, which I think is not that bad of a challenge, right? I've in the deeper past, you can usually modify some existing machine. I remember testing rubber bands by hooking them up on a milling machine, just sort of like stretching it a zillion times overnight. That's for a few tests. That's not bad. Of course, eventually you need to hire a professional, a fatigue-oriented engineer or a durability engineer or quality control type of a whole department really that are set up for this in the modern economy. Farther upstream of that is identifying where the weak points and the strong points of a mechanical concept are in terms of this durability kind of question. So, for example, we're our recent prototype of one of ours, we were like, okay, we'll just try this, these wheels and plates against each other in one purpose or another. And we knew from the outset that, you're not supposed to do that with aluminum on aluminum because that's not a good thing to do. But we're going to try it because we only need a few, tens of thousands of cycles or something like that. And we did, and we got wear all over the place. And so, we knew we were going back for another cycle and we'll do it better next time. But like, there's just this qualitative shift in even identifying all the places where, okay, we can make something work for a while, but is there a wear problem that's going to make it loose? Is there a property that's going to degrade? Any of these things that could be showstoppers when you try to go big or you try to go long term, right? And so those all have to be fleshed out, and you have to do your best at the appropriate phase in the cycle to evaluate whether there's an opening there or whether you've run into an impossibility where it'll only ever be a short-term kind of thing. So usually, I think there's a solution for that, but the mindset represents a sort of a wholesale shift in the way you have to think about the problem when you start addressing the long-term aspect.
I know we're spending a while on this, but I actually think it's really quite relevant, and I'm reminded of my experiences as a PhD student. So first, I'll tell that little story, which is there were all these great things about the Superfoot concept, which later became the Caplex system. I struggled with the same things that every engineer in an academic setting struggles with. Like you're describing with the aluminum on aluminum. I had tons of practical issues fabricating parts and building things in the lab. There was one particularly painful aspect of my design, which is that it involved a very small roller chain, which theoretically had multiple orders of magnitude more strength than I needed. But there was an issue with the way the tiny chain and the tiny sprocket wore and stretched over time that meant I had to replace chains constantly. It was very annoying. But the thing is, I didn't have the bandwidth in my day-to-day to do anything about it, right? So it was easier to just keep replacing the chain than it was to redesign the mechanism, which is proving to be, flawed. So I think that's one sort of aspect of technology development in an academic setting that sort of very frustrating. It's not like you're not solving a fundamental science question here, but it really limits fields like ours from progressing. And in my opinion, this comes back to sort of sources of funding. You are typically not given the latitude in a federal grant proposal, to hire an engineer who focuses on durability and maintenance and all of these things. It's just sort of very hard to budget for, but it's this bad chicken or the egg problem because I also think it's essential.
Yeah, I mean, those things are in practice in industry. You've got a large team, right? So there's one of those people doing that role for several products. You would never have an entire person for that on a staff of a very small one product team, right? You just can't justify that. So then what's your business and employment solution for that person and fulfilling that role? Not easy to solve, but people do. So that's something I think where the business world, people who know how to organize this are critical to making it go.
Not every academic PI wants to run their lab like a business, but in a field like this, I feel like many labs are being pushed in that direction, because you as a PI, naturally want to have the greatest impact possible, and there sort of tends to not be infrastructure to help with these problems. So yeah, I feel like I'm meeting more and more PIs that have like staff engineers who, kind of stick around across many projects. It can help build that institutional knowledge, but that's not always easy. Okay, so I wanted to touch on another subject you made me think of, which is that we're in this kind of dawn of a new era where, thanks to AI and rapid manufacturing techniques like 3D printing, I feel like there's often this notion, from people who maybe haven't lived it, that technologies now are easier than ever to kind of conceptualize, and you click print on the printer and you have a product that can kind of solve a pain point for an individual. To a degree, this is possible with the upper extremities, but with the lower extremities, it's sort of quite a bit more difficult. I was just at a national conference for orthotics and prosthetics in Indianapolis. Despite what I just said, we are starting to see some 3D printed lower extremity componentry, which I thought was pretty cool. I'm curious if those kind of techniques are kind of in your vision at all.
They are. A funny story about the difficulty of that kind of thing is that we recently went through a round of testing that involved printing a whole bunch of extra copies of something so that when it broke after 400 to 500 steps, we would replace that part and keep going until it broke again, and that's enough to do the science, and obviously nowhere close to having a commercializable kind of product, right? So we're rethinking that. That was our first foray into it. I think it has a great deal of potential, but the thing to remember is that you don't 3D print mechanisms very easily. You 3D print parts, and that most of the design optimization expertise in the world is about making things stiff and light. And that's not what we do in prosthetics. We make things springy and light. And those are actually very different directions to try to take a technology in. So, in recent rounds, we've tried to do some things with 3D printed continuous fiber materials and things, and they're great. They save a ton of weight, and yet there are really complex loading patterns and load paths, through these devices. It's really hard to make it strong in all the levels and layers and directions that you need. So we haven't had a lot of luck in my experience doing that. That's just with the additive manufacturing aspect. I'll defer on the machine learning AI kind of question, since I'm not an expert in that. I still need some growth myself. But I'll say one thing is that, such tools, the biggest thing is getting meaningful data for them to learn from. And I think that remains a giant challenge in a field where human subjects are hard to come by. Prior knowledge to put in to do any kind of synthetic data is hard to come by, right? So there have been some heroic efforts in the field to get big data sets. It's not clear to me how big is big enough for what kind of engineering you have to do to those data sets or to the studies that lead to the data sets in order to make sure they're appropriate to tell you something that you need to know. And of course, something you need to know is not a good way to phrase a question. You got to be much more specific than that at the outset. And I'm not sure our field is there yet, which I think is okay. I think many fields aren't quite there yet because the tools are so new and so disruptive.
I've in my free time dabble in photography, and I promise this is a related tangent. Photoshop, the software from Adobe, they're rolling out all these interesting AI-based tools and sort of help you clean up and edit your images. And it's incredibly powerful. I mean, there's tools where you can, circle an object in your photo and it just like gracefully eliminates it, or you can kind of roughly outline the background and replace it with something else. And at least in the demos, it's outstanding. Actually using it is a little harder than they make it seem. But yeah, I feel like with mechanism design, this is an area where mechanical engineers are still on their own. You might be able to use some automation to kind of shape optimize a surface, but to optimize a mechanism still seems to require a lot of sort of black magic on the part of the designer. And mechanical engineers that are really good at mechanisms are one of the hardest to come by.
Yeah, yes, they are. And I don't want to sell short the people who are working on these automated design kind of questions, because I think they have some really powerful thought processes that I'm not really familiar with, right? So I'm excited to see where that goes. A little nervous because I'm often uncomfortable with outsourcing decisions to things that I can't see inside, if you will, right? So, thankfully, I think people will be involved, if not forever, then for a very long time in that process. Hopefully, well-trained, competent.
I'll be watching with interest. So I want to pivot to your sort of other big line of work, which is around assessment. And I'll be honest, I haven't tracked this too closely lately, so I'm looking forward to getting caught up. How are you? Sort of what's the latest with remote sensing, or I should say, mobile wearable sensing? Yeah, whatever buzzwords you're using today, and kind of what are you hoping to accomplish with the technology?
Yeah, the key idea that we're going for with the mobile and wearable is to make actual measurements in the real world, and it's a legitimate question to ask why a person might want to do that, since the real world is wildly uncontrolled in many cases, and it can be very difficult to know what's in your data set when you take a data set from the real world, and it's very hard to do complete instrumentation on people in the real world. But nevertheless, I think there are things where there are a couple of flavors. One is if you want to study things in the lab that are relevant, you have to know what they were in the real world. And so traditionally we've done that by observation. We say, okay, people walk at, such and such a speed on about this distribution of level and flat, level and ramps and slopes and things. And so you take all those conditions and you put them back in the lab as best you can, study them. So characterizing what the world is in terms of the question you want to answer, in my case, all about locomotion. That's one reason to instrument people out in the real world. And so a few years back, Paul Slaughter, who's now working with Carl Zellick at Vanderbilt, he did a study on players in ultimate frisbee teams in competitive games, because a game is not a practice. Cutting in the lab is not the same as cutting when you're trying to score a point, right? And so he instrumented people in that situation. He got this great data set across different levels of teams and different competition scenarios and different positions on the team on cutting, right? And so that has the potential to inform what you study in the lab, as well as how you understand the importance of what you have studied in the lab in terms of real world movements. So that's one take. And then the other one is to see when you have generated an intervention, or say it's a new prosthesis, for example, right? What is that doing to people out in the real world? New prosthesis is actually very hard because you have to commit to setting it out in the real world. So we've been doing a study that uses a range of commercial prostheses of sort of different levels of features in the different sequence of feature growth, if you will, across a product line. And then another one with a couple of interventions for orthotics. And we're just trying to instrument as fully as we can the movements and, where possible, the loads on these limbs for long periods of time, on the order of a month, and try to understand how this works in real life, the effects of these things. Some of the preliminary findings from the prosthetics one are that it can take a week for a person to adapt to a prosthesis. And how do we know that? Well, we watched it day by day. Their knee angle trace does something totally different when they're walking in everyday life, day after day after day. And it does something different when you put a different foot on, and it does something different when you put another foot on. So, is that always the case? I don't know. We're still generating the data set, but that's what the first look at it showed. So that's important to know because it could affect prescription approaches and pattern of evaluation for care, and any kind of record you might want to generate to prove that what you did is good for a person, right? All these things will be influenced by knowledge of how that adaptation happens. The other question there is, how much instrumentation can you put on a person, and how do you do it? And so a bunch of my work has been trying to generate the right set, or a viable set of sensors that you can send out into the real world on a person, with and on a person, for these long periods of time. And so the prosthetic study has, I think, 4 IMUs on one leg and one wireless one on the other leg. And it has GPS, and it has some environmental sensors built in, which the idea there is to try and tell when a person has entered and left buildings, which are always, climate controlled and have pressure and temperature and humidity variations compared to the outdoors. We stick all that in there, maybe a load cell if you can fit it, and we just log. We take that and we
context.
Sorry, go ahead.
Yeah.
Do you want to?
Are you developing these sensor systems, or are you primarily talking about off-the-shelf sensors?
We've been doing a combination of that. So in the case we're doing here, we buy obviously existing chips, because you don't go. It's not my work to go down to silicon and design something new, right? But so existing sensors, and then we are developing the system that slurps data from them all into one place synchronously, and sort of assembles the whole thing. So that's like, what do? We took a little Raspberry Pi, one of the smallest ones, and embedded that as the central hub for everything, and just made it talk to a lot of off-the-shelf kinds of sensors.
Yeah, and this is, just for our audience's context, pretty high-tech stuff. I think, again, I was just at a conference recently, so memories are fresh in mind. You go to these conferences now, and I think everyone's used to seeing some kind of sensing technology, whether it's analyzing gait from a mobile phone, or it's one of these spandex suits that's covered in IMUs. This stuff is becoming more and more common. But your work is innovative in both in how the sensing technology is actually built, as well as, in the algorithms and kind of what you do with the data.
And that's because, I feel like as an academic, my role here is to envision the bloody edges of the space. Like, where should we be going with the next idea? So we do plenty of applied work using off-the-shelf systems, of course, when we want to know something that has sort of traditional questions behind it, right? And a type of instrumentation that can generate answers to those questions. But then there are all these things that nothing's appropriate for, like you put on the IMU suit. Well, that only lasts for 4 hours, and I want 4 weeks, so that's not going to do it, right? What is that factor? 168 times too short, or something like that, right? So then you have to do your own technology and push those limits? And so there are a lot of philosophical and practical questions like how many is enough? What could you learn from them? And what can you still not answer when you do this? And then above all, how do you reduce the data set into I can't just tell you a 4-week story about a 4-week experiment, right? I need to answer some questions in a couple of sentences. So how do you reduce it all the way down to that?
Mm-hmm. Yeah. That's the holy grail here is what is the actionable insight that is going to be easily interpreted by a decision maker, whether that's someone designing a prosthesis or trying to decide whether to approve or deny a claim for reimbursement. Could you talk a little bit about that? What are some of the insights that you've been kind of pulling out from experiments like this?
So that one that I mentioned a second ago, I'm really excited about this adaptation over time thing, because it's just so important to every aspect of prosthetics care. Is what is this? You and I have talked about it at great length, right? How do you optimize a prescription process so the right person gets the right thing quickly, but not so quickly that you can't make an adjustment, or not so quickly that you don't have the ability to recognize when it is or is not the right thing. And so I think that kind of insight into just, how does this adaptation work? How long do you have to wait? Where might you get better information about whether this is going to work or not? I think that's a place where it's going to have impact. There are also practical things like people with amputation, they fall a lot, right? That leg is just not as adaptive and aware and controllable as the other one. And so there's tripping, there's slipping, there are all kinds of things happen. And that's not great, right? That's dangerous and annoying. So in some of the work, we're looking at important metrics that are associated with that, like how high is the foot achieving clearance off of the ground during swing phases, for example. And that there are mechanisms explicitly built to lift the toe in different cases, and we want to understand how that's actually working when people are using these in real life. So these are a few of them. You could imagine, I'm not sure how many of these questions we'll be able to answer in the near term, but you can imagine things like how is variability affected, increased or decreased, and which of those is good, because even that is not totally known, right? Those and a lot more questions that we still have to formulate, we and others, from these long-term data sets.
Are you, when I first learned of this work some years ago, I recall a version of your approach where the sensors were sort of embedded in the shoes or at the feet. Is that still something you're working on, or do you feel like this provides such limited information that it's sort of necessary to instrument further up the body?
I find the feet to be incredibly compelling, and so there are big chunks of the work that still use that as one of the core inputs, I guess, to the data set. Partially because it's if you're using a reduced set of inertial sensors that doesn't cover the whole body, it's about the only part that you can rebuild accurately in terms of its movement is the foot. But if you do it, then you can go at least up that leg with the addition of more sensors. And so that's why we've got foot, shank, and thigh on the prosthetic side in our suite. Is that yes, the foot can give you this nice reconstruction, which is the older work that you're referring to. That's still the basis. But then you can go up to the shank and you start getting ankle angles, and you can go up to the thigh, and then you can get knee angles, and you can see the whole posture of the leg, and you can begin to do, the foot itself can give you things like stride lengths and such. So that's still in there as a key piece, but then you have to stop short of the whole set. And, we can put these on a prosthetic leg because you can leave them there overnight, and, it's not on when you take a shower, and, all these kind of things, right, that you couldn't do to a natural leg, which is why there's not the same stuff on the other leg. So there's this big dance of what's practical and what's beneficial. And you just have to commit to something, do a study, and see if it gave you enough information.
It turns out it's highly practical to have an IMU in your pocket, in your phone. But I might be getting the timing of this wrong. I think it was in the late 80s or early 90s. There was a patent for a smart shoe. Like the idea's been around for a long time, but it really hasn't hit mass market. It's a shame. I want sensors in my shoes. I hope you solve this one. If I wanted to acquire this technology in my lab, is that something you do? Do you build these systems for others to use?
Have not, but I probably would be willing to. Yeah.
We've talked about two very different paths of technology development. I'm wondering if you can kind of tie it all together for us, trying to understand, what makes Peter Adamczyk tick. What's sort of the mission and the fundamental, driving passion behind your work?
Yeah, I've been trying to keep that front of mind as much as I can in the day-to-day details or through the day-to-day details. I want to help people move better, with legs. So I'm highly motivated in my own life by the idea that that moving a lot keeps people healthy and happy over many decades of their lives. And the longer that lasts and the healthier it is, in many ways, the better your life is. And so that's obviously not a universal thing. And I don't mean to be ableist, right? But I do mean to be enabling wherever possible for people to enjoy these activities that are so common and so rewarding. So making people move better, helping people move better through technology, and particularly in the case when they have some kind of impairment. That's what makes me tick. And so there's an understanding side of that. There's a technology side of that. There's a strategies for intervention side of that. And there's a place where all those meet, which is probably in professional practice of a clinician, right? Which I am not, but I'm essentially hoping that the sensing, the technology, the practice, rehabilitation techniques, personal management, all these things come together in ways that where better decisions can be made by professionals and then by individuals in an ongoing way.
So for folks who want to participate in this with you, either as potential collaborators or perhaps students, what's the best way to contact you, and how do we find you on the web?
So my lab website is at the University of Wisconsin. We're called the UW Badger Lab. That stands for Biomechatronics, Assistive Devices, Gait Engineering, and Rehabilitation. So you can Google that or do uwbadgerlab.engr.wisc.edu. Best contact is probably my email, which you can find there as well. I'm on LinkedIn, and any member of my team is available on the web as well if you find a project
wonderful
that you'd like to find.
And then closing, Peter, I was hoping you could share a call to action with our audience.
Get out there and be moving as much as you can. Keep yourself young and healthy, and I'd say, from my perspective, think carefully about how you're doing it, because that is going to help you make wise decisions and give wise advice to others to live long and healthy lives.
I love it. It sounds simple, but it's easier said than done. Good luck, everyone. All right. Thanks, Peter. This has been fun.
My pleasure. Thanks for having me, Josh. Thanks for the good, hard questions.